This is what a mission to Venus looks like. How did we get here? What are the design stages involved in creating such a high-risk mission? Follow our team on this presentation of our final Aero 251 design project at Purdue University.
This mission is an innovative, cost-effective, and reliable transportation system for delivering highly advanced scientific discovery technology into deep space and back to Earth. The payload that is required inside the vehicle is a 20-kilogram probe and a 1-kilogram instrument to search for organic chemicals in the clouds of Venus and explore the atmosphere's habitability, which together make up the nuclear thermal propulsion system.
The main stakeholders we identified for our mission include Rocket Lab, who's our main client, investors of the mission, the actual rocket designers, and aerospace enthusiasts. To satisfy these stakeholders, we create a list of requirements for our mission, including having adequate fuel, high propellant efficiency, while keeping a reasonable cost. Some of the main risks we identified for the mission include heat and harm of the module when entering and exiting the atmosphere of Earth and Venus, failure of the nuclear thermal propulsion system, and obstacles and space debris upon others. To mitigate these risks, we will design a strong heat shield capable of protecting the inner electronics of the spacecraft, design the NTP system to run off more than just hydrogen as fuel, track space junk and asteroids to avoid possible damage, and choose strong, heat-resistant materials to avoid corrosion and radiation.
The total delta V required for travel from Earth to Venus's atmosphere is 15.68 kilometers per second. This delta V can be broken down into delta V Leo, the velocity needed to get into an orbit around Earth, delta V1, the velocity needed to initiate a homotransfer, and delta V2, the velocity needed to exit the homotransfer and enter an orbit around Venus. To calculate delta V Leo, the V-circ equation was used, and then V loss and V Earth help were taken into account. The result was delta V Leo equals about 8.9 kilometers per second. Next, to find delta V1 and delta V2, the hyperbolic excess velocities were calculated. The hyperbolic excess velocity is the velocity a body will attain if it travels along a hyperbolic path for an infinite distance. Then, by applying the concept that specific orbital energy is conserved, the velocity of the rocket while in the transfer orbit can be found. This is called V-hype. Finally, delta V1 and delta V2 can be found by subtracting the velocity of the rocket while in orbit from V-hype. Delta V1 came to 3.48 kilometers per second, and delta V2 came to 3.32 kilometers per second.
In the optimization program, Stage 1's ISP was around 375 seconds. This value was based around the standard ISP for the liquid hydrogen and liquid oxygen propellant. The second stage has a liquid hydrogen NTP propellant because it is the propellant required by the mission. The initial weight of Stage 2 is around 360 kilograms, and of Stage 1 is around 4,700 kilograms.
We considered two launch sites, Cape Canaveral and Boca Chica. We came up with these locations because both are well equipped with existing launch pads and close to the equator. We selected Cape Canaveral because it offers the highest Earth help velocity and more reliable launch pads operating since the 1960s. In order to develop a launch vehicle concept, we compared 4 existing launch vehicles. We examined NASA's Saturn V, NASA's Delta IV, SpaceX's Starship, and Mitsubishi's H-2A rocket. We selected the Mitsubishi H-2A to reference for staging and sizing. However, we selected different propulsion systems, most notably the NTP system for the second stage. This helps meet the criteria for minimizing inert mass because nuclear propulsion is known to allow a lower total mass to be assembled for a given payload mass. We analyzed 3 sets of orbits to move from Earth to Venusian orbits: low Earth orbit, medium Earth orbit, and a direct launch to Venus. We calculated delta V required for each option and selected LEO for this mission. This meets the criteria for lowest delta V option available and reduces costs. Finally, we created the design concept shown here. To dimension our rocket, we predicted the volume of each stage and maintained a constant diameter to solve for the height of each stage. The first stage of our rocket will be 4 meters in diameter and 31.5 meters tall. The second stage of our rocket will be 4 meters in diameter and 9.3 meters tall.
To conclude, one of the most important lessons learned from this project is the variety of factors that go into evaluating a rocket design for launch, such as attitude control failure, vehicle breakup during liftoff and ascent, among many others. These evaluations can only be made past the conceptual design phase of the engineering design process during part testing. Our proposal is only a few steps away from successful testing, making our design a go for launch.